All right, we are recording. Um, I'm going to be posting a new homework assignment, and this will be over electric potential, the topic that we're starting today. I don't have any homework problems for you on Gauss's law, but good things to practice would be the examples that I've done on the video, so you could try those out on your own. Anyway, today we're starting uh, the study of energy in electricity, and we call that electric potential. But I'm going to back up a little bit and talk about some of the energy things that we did earlier, although we didn't put a lot of stress on it. And one of them was that the change in potential energy when you're dealing with a force is, and this would be for who knows what, it could be like the gravitational force, maybe lifting an object in the gravitational force or letting it fall, but it's defined to be the negative of that force times the displacement along some sort of a line. And so you'd be going from some initial point to some final point, and it's got this minus sign out front. If you are going in the same, if the displacement is in the same direction as the force, you're kind of going downhill with the force. So this would be like the gravitational force is pointing down. If your displacement is also down, then this F dot ds is going to be positive, but you've got a minus sign out here. So you'll actually be decreasing your gravitational potential energy if you're going down toward the surface. If you're going up, then F is pointing down, but ds is pointing up, and so that dot product is negative, and negative in here, but a negative out front, you'll be increasing the potential energy. So that's something that happens with changes in potential energy between 2 points. And this relation happens to be true no matter what the force happens to be, whether it's gravitational potential energy or spring potential energy or electrostatic potential energy, which is the topic we're going to be studying here. One of the first things we'll look at is the change in potential energy for bringing two charges close together. And let's just suppose that we have a charge Q1 sitting over here and a charge Q2 sitting over here. And initially, they're separated by some distance, which we can call R initial, and I'll make dots for the two particles. And then in the final situation, we're going to have them separated by a much smaller distance that's only going to be R final. So, and then this would be Q1 and this would be Q2 here. And we can imagine that somehow we hold Q1 fixed while we're doing this. And so we're bringing in Q2 here. Well, we know what the electric force is going to look like in this case. It'll be the force that's acting on them is going to be K sub E, Q1, Q2 over R squared along R hat. And if they happen to be the same charge, then R hat might be pointing out in this direction. Well, actually, R hat is pointing in that direction anyway. As long as they're the same charge, the force will be in that direction. If they're opposite charges, then this product would be negative and you'd actually have it in. But let's see what can happen here. I'm just going to move along a straight line here as I'm coming in so that ds as a vector is going to be minus ds in the r hat direction. And so when I do the dot product, f dot ds, I'll have this stuff that's going to stay constant, not all the time, but K sub E, Q1, Q2 over R squared, and then that's along R hat, and I'll be dotting that with minus ds in the R hat direction. R hat dot R hat is 1. A unit vector dotted with itself is always 1. I could think of this ds as also equaling dr. So I can, it's going to equal dr, but what I get out of all of this is that the f dot ds part is going to equal K sub E, Q1, Q2 over R squared, and I'll have dr, but I'll get a minus sign out of this. And so I'll be going in that direction. And I hope I didn't introduce too many minus signs or not keep track of all of them. But let's see what happens here. I'm going to go from an initial R initial to a final R final. So the change in potential energy here would be the negative of this force. So in this case, it's going to be plus because I've got a negative integral there. So R initial to R final, and K sub E, Q1, Q2 over R squared dr. And I probably got a minus sign wrong on here somewhere. Losing, possibly doing this. But we'll see what happens here anyway. This stuff in the numerator I can pull out, and so what I'm actually integrating is going to be the integral from R initial to R final of dr over R squared, which is going to be, well, the integral of that is minus 1 over R. So I've got the K sub E, Q1, Q2, and then minus 1 over R evaluated at R initial and R final. Okay, all of this just to figure out the work done in here, but actually once we're done with it, well, with the minus sign there, what I can do is actually reverse the order of the at which I evaluate this, and so I'd end up with K sub E, Q1, Q2 times 1 over R initial minus 1 over R final, and sure enough, I think I did get an extra minus sign in here somewhere. I probably should have had ds being the negative of dr, because ds points, well, I kind of had it that way. Okay, 1 over R initial, yeah, this would be a small value minus a bigger value. So that'd be negative. And this should actually increase. So let's put a question mark by that, because I think I should have had a minus sign, in which case this would be a minus sign, this would be a minus sign, this would be a minus sign, and I'd actually have plus 1 over R when I consider two minus signs, and it should have been 1 over R final minus 1 over R initial. And let's see how that looks if I fix it that way. Slide this up a little. See if the delta U makes more sense in this case. I'd end up with K sub E, Q1, Q2 over R final minus K sub E, Q1, Q2 over R initial. This is the change in potential energy, which in this case would be U final minus U initial. And I could actually kind of define, oh, well, it's easiest to define changes in potential energy, but what we like to do often is select some point where the potential energy is going to be zero and then measure everything relative to that. But what we have here is going to work okay. Anyway, this will be an increase in potential energy because the R final is smaller than the R initial, which means 1 over R final is going to be bigger than 1 over R initial. And so this would be a positive change in potential energy. And if the two things are the same sign, this will be positive, this will be positive. And so bringing them together, I'll be increasing the potential energy. It's like compressing a spring, although it's not quite the same relation. Actually, yeah, it's not quite the same relation, but it's compressing a spring is what you're doing in effect. And bringing them together, you have the potential to do work on them and give them kinetic energy, because if you bring these two charges together and let go, they'll spring apart. So that's what we'll have going on here. All right. However, well, we can talk about the potential energy of two charges. In fact, what we do is we select the zero of potential energy for two charges, electric potential energy, to be such that this ends up being the potential energy of those two charges. And the way we do it is to actually define the potential energy to be zero when they're infinitely far apart. And so the first one, that the R initial would be infinity, which makes this term zero, and this would be the final energy. So for electrical energy, our choice is usually going to be to define it to be zero at infinity, although not always. Sometimes we'll define some point in a problem to be zero, especially in electric circuits. But for now, we're going to have K sub B Q1, Q2 over R would be the electric potential energy of two charges. And this is similar to what we had for gravitational potential energy, although when we studied gravity winter quarter, we defined the gravitational potential energy to be zero at infinity. But that's an attractive force. Electricity can be either attractive or repulsive, and so you can have positive gravitational potential energy, which didn't work so well when we were considering things like putting stuff in orbit and making it escape and things like that. But let's try an example problem that'll use that relation. We have two charges separated by 5.00 nanometers. One of the charges is plus 2e and the other is plus 1e. And just as an aside, what do you suppose these things are? What might have a charge of plus 1e? And what might have a charge of plus 2e? And I'll let you just kind of stew on that. But in this case, the potential energy of these charges would equal K sub B. Let Q1 be the 2e. Let Q2 be the e. And remember that e is the charge on the fundamental unit of charge, 1.60 times 10 to the minus 19th coulombs. So something with a charge of 1e on that would be a proton, actually. Anyway, and we're going to divide by that separation, just the r that we have there. And so I'd have K sub B is 8.99 times 10 to the 9th Newton meter squared per coulomb squared. And then I'll have E squared here, but I've got a 2 in there as well. So punch in the E, 1.60 times 10 to the minus 19th coulombs and square that. And this will give me coulombs squared. That'll give me coulombs squared, and I'll have Newton meters squared, period, there. But I divide by the distance between them, which is 5.00 times 10 to the minus 9th meters, or nanometers. And one of those meters squared divide with that. So I'm left with Newton meters, which are joules. And so that's the units we'll end up with here. And let's see how much it is. 8.9. Okay, not much. I get about, I guess I can keep 3 sig figs on this thing. 9.21 times 10 to the minus 20th joules. Turns out that joule is not a convenient unit when we're talking about small charges, things that might have a charge of 2e or 1e or something like that. But I'm going to wait for the next problem to introduce the unit that does happen to be convenient. And so we'll deal with it that way. Okay. Here, an electron and a proton are separated by 5.29 times 10 to the minus 11th meters, the distance referred to as the Bohr radius, because in Bohr's original model of the atom, it was the radius of the lowest energy electron orbit. What's the electric potential energy of this system of charges? Okay, well, it's going to be that expression that we just had there. The U is equal to K sub E Q1, Q2, and in this case, the Q1 and Q2 are going to be a plus E and a minus E. And then we just divide by, in this case, R sub B, the Bohr radius is what this thing happens to be. Okay, and it'll be minus KE squared over R sub B. So let's see what comes out of this. Minus 8.99 times 10 to the 9th Newton meters squared per coulomb squared. And I'm running out of room here, of course. I'll just stick something else under there so I don't ruin my pristine white sheet that's under there. Times 1.60 times 10 to the minus 19th coulombs squared again. And then R sub B, the Bohr radius, 5.29 times 10 to the minus 11th meters. And so the electric potential energy of this combination of charges should work out. Okay, this will be minus 4.35 times 10 to the minus 18th joules. And again, a joule is not a particularly convenient unit for dealing with electric potential energy in an atom or any kind of energy in an atom. It's just too big. However, there is another unit of energy called an electron volt, and 1 electron volt is equal to 1.60 times 10 to the minus 19th joules. So that's a way to convert it into a unit that's a little bit more convenient in this case. Now, this is no accident down here, and I'll talk about where the electron volt comes from in a little while. This number is the same as the charge on the electron, and I'll explain what's going on with that. But if I divide this by 1.60 times 10 to the minus 19th joules, I'll get something that's not quite so tiny. Man, I get about 27.2 minus 27.2 electron volts. If you've taken a chemistry class, you might have learned about the Bohr atom, but you probably didn't see that number in there. This is the electric potential energy of the electron that particular distance from the nucleus of the atom, but that's just its potential energy. It also has kinetic energy, and the kinetic energy of the electron in that particular state happens to be positive 13.6. Excuse me, I was doing something in my head and didn't get it right. And when you combine the kinetic energy that it has with this electric potential energy, the total energy is equal to the U plus the KE, and it ends up being minus 13.6 electron volts. And that may be a number that you might remember if you've taken a college chemistry class. I don't know, I don't remember ever doing that in my high school chemistry class, although I took it so long ago, I don't remember much of what we did in that class, except, let's see, I can't remember the guy's name. Vetilago, maybe? It was an Italian name, whatever it happened to be. Okay, anyway, there's just a couple of electric potential energy problems. Now, we don't usually calculate electric potential energy for things, or sometimes we do it, but we go about it from a different direction. And I want to show you the direction that we take for this. Keep in mind that delta U for some particular charge configuration, actually what we'd be doing is minus the integral of, we deal with electric fields and not forces typically. So we might have QE dot ds for being the change in electric potential energy of something. And electric field, remember, was the force per unit charge on something. Well, this thing's not going to affect the integral because it's a constant. We can pull it out, and so we can have minus q times the integral of E dot ds. But fortunately, or frequently, we're more interested in this thing than the actual change in potential energy. And so we might actually divide both sides by this Q. And what we get when we do that is delta U over Q. This would be the potential energy per unit charge. And then in the geometry we have that we're calculating this integral for, we'd get a change in potential energy per unit charge, and we could think of, maybe we'll let that force act on a proton. Maybe we'll let it act on an electron. Maybe we'll let it act on an alpha particle or something like that. Could be any different kind of charged particle. And so what this will equal is the negative of the integral of E dot ds. And we're going to define this to be the, now be careful with this. This would be electric potential energy, the delta U. This we call electric potential. And it can be confusing. Electric potential. Okay, this is electric potential energy. So this is the potential energy per unit charge. And so we've got weird stuff in here. And this is independent of the charge that you take across that thing. If we want to know what the change in potential energy is, we do something like just do this. Take whatever charge you have and multiply it by the delta V that you're happen to get. In fact, sometimes you might say an electron is accelerated across a electric potential change of so many units, and I'm going to introduce the units here very quickly. What will be its speed when it arrives at the final destination? So we might be given this value and told what the object happens to be, then you just multiply them together to get that. And that change in potential, electric potential energy, would equal 1/2 mv final squared minus 1/2 mv initial squared. You may recognize that. That'll be the change in kinetic energy for the thing. Now, what about units? Okay, this is going to be joules up here. Charges we're going to measure in coulombs, and units of potential are joules per coulomb, and those are volts. That's where volts come from. You've heard of them lots. If you plug something into the wall, it's usually 120 volts, but it's alternating current, so it keeps changing sign continuously, something you may not be familiar with. Typical AAA or AA battery has a potential difference between the two ends of it of about 1.5 volts. You can get 9-volt batteries. That's the difference in electric potential between the two sides of it. And so it's a term that you hear all the time, but this is where it comes from. And it's electricity is one place where in the United States we use the metric system all the time. And that's kind of nice. So the units that you're going to use in here, you won't have to worry about. Now, we also want to select a 0 point for electric potential energy and electric potential. And most of the time, for most charge distributions, we usually, and I'll say usually because sometimes we don't, V is equal to 0 at infinity. Often we're just interested in delta V's, differences in potential energy. So then it doesn't matter where the thing happens to be set equal to 0, the difference is going to be the same every time. It's like on the Celsius scale, a temperature difference of 35 degrees Celsius is also a temperature difference of 35 Kelvin, even though those temperature scales have their zeros set at different points, it's still the same difference. And so a delta V is the same no matter where we set it to be zero at. But a lot of times it's convenient to set that equal to zero at infinity. And then the potential difference between infinity and a point would look like delta V is minus the integral from infinity to some point P of E dot ds. And when we do that, we find out that the electric potential of a point charge ends up just equaling K sub E Q over R. Okay, if Q happens to be a positive charge, this is going to be a positive value. You can't have a negative R when you're talking about a distance here. So if it's positive, and it also blows up as you get very close to the thing. And so the electric potential of a positive charge, you make a graph of V versus R, it blows up when you get close to the thing. If it's a negative charge, it drops down. It's just a mirror image of this reflected across that line, but that's what it might happen to be. Something nice about this, it's a scalar, and so you don't have to worry about vectors when you're calculating electric potential. You can also calculate the electric potential of a bunch of different charges, like grab a new piece of paper. If you have a whole bunch of charges and you want to know the electric potential of those, it can just be the sum from I equal 1 to however many charges you have of K Q sub I over R sub I. And this would be like if you've got some point P that you're calculating the electric potential at, and you've got a Q1 here, and a Q2 here, and a Q3 here. This distance would be R1, this distance would be R2, and this distance would be R3. But all three of those things are just distances. They're not vectors. And so you don't have to worry about directions and components of forces or anything like that. It's just a nice scalar calculation. If you have a charge distribution and you want to know the potential of that, you change this sum into an integral and you just go K sub E dq over R. And R is something that's going to be changing depending on which chunk of charge you happen to be dealing with. But again, it's just a distance. It's not something that you have to get components of. So some of the calculations with electric potential are going to be easier to deal with than what we've done so far. Well, okay, let's see, that looks like 2 blank pages. Let's see what, something else I wanted to talk about was the definition of the electron volt, which we already used, but I can give you another expression that will help understand it a little bit. And I don't remember if I gave you this is the abbreviation for an electron volt. By the way, the volt is the unit that we use for measuring electric potential. So capital V would be that, but capital V is also what stands for the electric potential. So this is kind of an inconvenient thing, but you get used to it. And since so often we'll be talking about a delta V, that'll be the change in electric potential, and hopefully that's not too confusing, but it'll be the change in volts too, because the units are in that as well. All right, but the electron volt, it's a unit of energy. And when we take a delta V and multiply it by some amount of charge, we'll get amounts of energy. If you measure the charge in coulombs, you would get coulombs times joules per coulomb, and you'd get joules for the energy. But sometimes you just measure the charge in electron charges, and if you multiply that by a potential difference, 5 electron charges or 3 electron charges, you automatically get units of electron volts. And here's what the electron volt is. 1 electron volt is the energy acquired. You think of it as the kinetic energy by an electron when accelerated through a potential difference of 1 volt. Okay. So if it's going to be accelerated, that is sped up. If you're in some region where you've got an electric field that's pointing in this direction, remember that's the direction a positive charge would get pushed. If you had an electron sitting here, it's going to be pulled in the opposite direction. And if the potential difference between here and here happens to be 1 volt, and that delta V is going to equal the negative of E dot ds. Okay, so you'd calculate this. But anyway, if this is 1 volt of potential difference between these two sides, if the electron starts over here at rest and ends up smacking into the wall over there, it'll have 1 electron volt of energy when it smacks into the wall over there. So that's what it happens to be. So you can think of it, try to think of it that way, I guess. Okay, I think I've got a couple more example problems we can do here. Oh, about electric fields. The electric field definition we've been using is a Newton per Coulomb, and our ds would be in meters. So this, the units on this side of the equation are going to be newtons per Coulomb times meters. And these are the units we've been using for the electric field. Well, over on this side, we've got volts, and that capital V is the symbol for a volt. Well, if we divide both sides by a meter, I get that a volt per meter is equal to a Newton per Coulomb. And so we can measure an electric field in either newtons per coulomb or volts per meter. They're identical. And it's actually more common to measure electric fields in volts per meter than in newtons per coulomb. So keep in mind that these two things are the same. And so we can hop back and forth between those. Okay, which is why in this problem you have a uniform electric field of magnitude 250 volts per meter. It's directed in the positive x direction. So if this is y up here and this is x, the electric field is pointing in that direction. and it's got that magnitude. A plus 12 microcoulomb charge moves from the origin, here's the origin down here, to the point X and Y is 20 centimeters and 50 centimeters. So let's suppose this is 20 centimeters, then 50 centimeters is going to be about up here. And it moves up to there. What was the change in the potential energy of this charge? Well, here's sort of an easy way. This is a positive charge. Okay, if the electric field is pointing in that direction, the direction of the electric field is pointing downhill in potential energy for a positive charge. And this is a positive charge. Okay. Now, the displacement of this thing is going to be here. This will be delta R, and the change in position, delta R, is going to equal, I'll write it as 0.20 meters. Maybe I don't have two significant figures. Well, I got 2 on that and 2 on that, so I'm going to pretend that I have 20 on the, or 2 on that. It'd be 20 meters along I hat, or 0.20 meters, plus 0.20 meters or 0.50 meters in the J hat direction. So the change in potential energy here, when we've got something where I have a constant electric field, I can just say that delta V is going to equal minus E, this is constant, dotted with delta R. And it's usually minus E dot ds, but I have a constant electric field, so I could pull it out of there, and ds would end up, the integral of ds would end up equaling dr, or delta r there. All right, well, it said the electric field points in the positive x direction, so E, I can just say, is equal to 250 volts per meter in the I hat direction. So my delta V here, change in electric potential between this point and that point, is going to be the negative of 250 volts per meter in the I hat direction, dotted with 0.20 meters in the I hat direction, plus 0.50 meters in the J hat direction. And let me shut a door real quick. Okay, just looking at the dot products here, I distribute this through that sum over here, but this one dotted with that, I hat dot I hat is 1. This one dotted with this, I hat dot J hat is 0 because they're perpendicular. And remember, the dot product has that cosine theta term in it, which is the angle between this vector and that one, and the cosine of 90 degrees is 0. So I only have to consider the displacement this way. Going this way, perpendicular to the electric field, I don't have to worry about any work done. So that's what I'll have. So I'll have 250 volts per meter times 0.20 meters. You can do that in your head. It ends up being 50 volts. So the change in potential is minus 50 volts. And that's a scalar now. So I have that. Now the change in potential energy of the charge in that case, well, this is delta U, which is equal to Q delta V. Keep in mind that thing. That's a fundamental relation, or delta V is delta U over Q. Change in potential energy per unit charge is what change in electric potential happens to be. So in this case, I've got plus 12 times 10 to the minus 6 coulombs times negative 50 volts, but a volt is a joule per coulomb, and 50 times 12 is about 600 times 10 to the minus 6, which is, oh, I don't feel like doing this today. Anyway, I think it's 6 times 10 to the minus 4th joules, but it's negative. Minus 6 times, and I do have just kind of, maybe I could think of that as two significant figures. 6.0 times 10 to the minus 4th coulombs times joules per coulomb, that'd be joules. Although I may have gotten a decimal point wrong there, but I don't think so. Let's see, let's do 12E6 times 50. Oops, how about 12E minus 6? Yeah, 6.0 times 10 to the minus 4. Okay, so that's part of it. For part B, what have we got here? Through what potential difference? Oh, I already figured this out. What potential difference did the charge move? It's minus 50 volts. So I'm not sure why they asked them in that order, because it's easiest to figure out the this thing first and then figure out this thing. Although I guess you could do delta U equaling Q delta V, and for delta V have minus E dot delta R. Could have done that first. So we have that. Oh, okay, here's one. This is for an old-fashioned TV set, but the difference in potential between the accelerating plates of a TV set is 25,000 volts. If the distance between the plates is 1.5 centimeters, find the magnitude of the electric field in this region. So what you have is that you've got these accelerating plates and a beam of electrons gets shot into this region. But anyway, the delta V here is actually 25,000 volts. And because you're accelerating electrons, this is the high part of the potential, and this is the low part of the potential. But when you stick a negative charge in here, it goes opposite the electric field. So the electric field here points in that direction. And it's, you can think of it as being constant if you want. Let's see, doesn't say that, but when you have plates like this, actually I've way exaggerated the separation as opposed to the sides. They're more like things that are like this, pretty close together like that. And when that's the case, the electric field between the two plates is relatively constant. And so we have the delta V, which you can think of as being E delta X, and that's the separation between the two plates. And so the electric field ends up equaling delta V over delta X. And in this case, we're just dealing with magnitudes. I'm not so worried about directions here. I'll have 21 volts over 1.5 times 10 to the minus 2 meters. And let's see. And I get 1.0 times 10 to the 6th. Hope I did that right. Oh, no, it's not. I don't know why I put 15,000 in instead of 25,000. Okay, 1.7 not 1.0, 1.7 times 10 to the 6th volts per meter. Okay. Here's a question. Maybe this is something I'll ask tomorrow. I can't remember. Or later. No, it'll be a similar problem. But how fast will an electron released from this point be going when it hits that point? Okay. Well, oh, by the way, I looked up the breakdown electric field strength for air, and I wrote it down somewhere here on one of these sheets of paper. I can't remember what it was. I think it was 3 million volts per meter. Yeah, it is. The breakdown strength of air. And so this is getting close to that, except that the tube in which the electrons were traveling is actually a vacuum tube. And so there isn't any air in there to break down if you were to happen to increase this voltage significantly. So when I was a kid, we lived on the kind of the outer outskirts of Spokane, and there's a place that we used to like to go all the time, and it was beyond the outskirts, so you're kind of out in the woods, the Ponderosa pine forests there. And it was a place where a lot of people would go out there and just dump garbage instead of paying to take it to the dump or something. And one of our favorite things to find was old TV sets, and we'd throw rocks at the TV tubes. And when you broke it, broke the seal in the glass somehow or cracked it like that, it would implode and it would collapse inward on itself because it's a vacuum inside there, and you all of a sudden let air flow into there. So, but new TV sets aren't nearly as much fun to throw rocks at. Not that I haven't done it, but they don't have vacuum tubes anymore. But here's a simple problem. How fast is the electron going after crossing the divide? After accelerating across this potential difference. Well, how much energy is it going to have? Well, let's see, the change in potential energy for the electron, this will be a decrease in potential energy actually, because a negative charge actually has more potential energy here than it does over here. If you were taking a positive charge in this direction, going against the electric field, you'd be going uphill and it would be gaining potential energy, but the electron is losing it. And so that will equal Q delta V. Now, if I measured the Q in just electron charges, I would say that the electron would have 20,000 electron volts of kinetic energy when it crosses this region. But I'm going to do it in joules per coulomb so I can actually calculate the speed of the electron. And the Q delta V is going to be, the charge is minus 1.60 times 10 to the minus 19th coulombs, and I multiply that by the 25,000 volts, which is a joule per coulomb. And so it'll tell me how much potential energy it's lost, but that'll equal the gain in kinetic energy. And if it starts from rest, 1/2 mv final squared minus 1/2 mv initial squared, this will be 0 if it starts from rest. And so that'll equal this product here. but changing the sign on it, because this is the lost potential energy, which is equal to the gain in potential energy magnitude wise. So $5,000. Then I get 4.0, should have been able to do that in my head, times 10 to the minus 15th joules. Okay, well, another blank page here somewhere. Lots of them. Going through paper like crazy today. Oh, well, I'll just do it on this mostly blank thing. Whoops, this is V final here, not V initial. Can't have two V initials. Anyway, V final will equal 2 times that thing. So 2 times 4.0 times 10 to the minus 15th joules divided by the mass of the electron. I've got it memorized. You guys would have to look it up probably, but 9.11 times 10 to the minus 31 kilograms. And this isn't something I've tried to memorize. It's just stuck in my head after doing a zillion problems with it. And I have to take the square root of that. So this would be, I still have that in there. And I get, whoops, I forgot to raise that to the 1/2 power. Got something going a whole lot faster than the speed of light, which isn't quite possible. Okay, but it's going a pretty good clip. It's actually about 9.4 times 10 to the 7th meters per second. Remember, C is 3 times 10 to the 8th meters per second. So this is going, let's see, about 30% the speed of light, which means we'll learn next quarter, you'd have to take into account relativistic effects when you try to bend the path of this electron in the TV set. So that's a place that the engineers who designed TV sets would have had to include special relativity in their calculations. Let's see. That's another example problem, but I think I'm going to stop there. I'll leave this one for you to try on your own, and it's not hard after having done the problem that we just did. So yeah, go ahead and try that one on your own. Any questions? Haven't seen any pop up, so have a good weekend. Stop the share there, end the recording and the meeting.